is going to tell us more of his continuing quest to fix literal notation.
Okay, thanks. So this paper is based on, on work that I did during my PhD at CMU last year. I'm now a postdoc at U Chicago on the job market. And I've continued to spend a little bit of my time on this project, namely on integrating some of the design work from that thesis into OCaml by way of Facebook's new Reason front end for OCaml. So this paper covers that whole span of work. So as a researcher, I'm really interested in programming languages in their capacity as user interfaces between human programmers and mathematical structures of the various types that can be expressed in the semantics of the language. So for example, you can express lists in many languages as an inductive data type with nil and cons constructors. You get nice induction principles that way. But notationally, as a user interface, there's really something to be desired here when you construct and pattern match on lists in this way. And so many programming language designers recognize that, and they include list literals, list literal notation in their language, provides a more clear and concise alternative notation for constructing and pattern matching on list values. So this is a really common feature. Lists are a common data structure, but increasingly languages are adding literal notation for other data structures. So several languages now have HTML literal notation. So if you have a data type that has these constructors like h1 elements and text node, well, that gets pretty inconvenient. And moreover, there's a standard notation for HTML that programmers are familiar with. There's consensus there, right? So these languages have these literals that are based on the HTML standard, extended though, because we're working in a programming language, we're constructing these values programmatically with what we'll call splicing or splicing forms, which allow you to mention sub-expressions of various appropriate types within the literal. So here, this is a splice string form, and it just means that that expression name is going to appear automatically with this text node constructor around it in the corresponding part of the expansion. So, concision familiarity, there's also security benefits here. If you're familiar with injection attacks, this prevents them because you're not doing stringly type programming here. This is actually just an alternative way of writing exactly those constructor applications where in that representation, text nodes are different from script tags, and so you can't get these injection attacks as easily. So that's just a couple of examples of literal forms. There's many more possibilities out there of data structures that might benefit from literal notation. For example, things other than lists, containers like dictionaries, things like regexes and SQL. Little data structures like dates and times and URLs and paths. We did a little study in a previous paper, where we looked at how strings are used in open source code, and it turns out a lot of strings are being used to actually encode this kind of data. It'd be better if we had composite representations of this data with notation, right? If you're a PL person, you're writing a compiler, you have an intermediate language, you might want the concrete syntax for that, this quotation idea. And then from science, if you're a chemist, there's this notation SMILES for chemical structures, and you might want to work with those chemical structures in your language. So we could start asking our language designer to start adding these notations to the language, corresponding type definitions to the standard library. But this starts getting pretty precarious. You got to make sure these things don't overlap. Once it's there, you can't take it out. And so I think this approach is clearly unsustainable. A better approach is programmable syntax, where library providers have the ability to define literal notation themselves because they're the ones defining these data types, right? So this has been studied by various people. One mechanism is just this direct syntax extension mechanism, which you allow library providers to just directly define new non-terminals that get added to the grammar of your language when the library is imported. So here we have a number of libraries that we're assuming have been imported, and then a little snippet of code that uses a couple of the notations that these library providers have added to the grammar. So this, from the perspective of a library provider, this gives you a lot of power. But I think one of the lessons of language design, in the last couple of decades has really been too much power isn't really always a good thing. And the way we can understand that is let's consider the perspective of a client programmer. I'll represent as this confused-looking owl here. And the owl is confused because it doesn't quite recognize that notation on the third line. What is that? It must have come from one of those libraries. Who's responsible for this mess, right? Where is this form defined? Which of these libraries came up with this? And it's hard to tell because it's just a global addition to the grammar of the language that's happened there. Even if we look at the first one, maybe we're familiar with HTML, but actually if you look on the On the right there, XML has also been imported. Are we sure it's HTML? Could there have been conflicts? How were those resolved? Some confusing way, probably. So there's questions of responsibility there. And then a bunch of questions about just types and binding. What is the type of the expansion of one of these literal forms? It's difficult to answer without looking at the expansion or implementation of the parser. What assumptions, what dependencies do these expansions have? Which libraries do they need to have in scope? Which names do they need to have in scope? Difficult to answer without looking at the expansion. And then where are these sub-expressions? This notation, how do we know that this character sequence name up there is actually an expression name and hello isn't and H1 isn't? And what are the X's and the 2's and the R's doing there? Are those variables or what are they, right? So the question is, where are the splice expressions? And even if you know where they are, what types should they have? How do we know 2 curly braces means string? And where are the variables inside those splices bound? Do we know that that variable name is bound to that argument name of that function there? That's reasons notation for functions. Or could it have been bound accidentally to some other binding of name internal to one of these expansions that you're not seeing here? This is really, these questions are about abstract reasoning. Can we hold abstract the implementation of the parser and the expansion and just look at the program itself as it's presented to us and answer questions like these? And the answer with these mechanisms is no. And so this paper introduces this mechanism, type literal macros, which allow you to define these new literal notations of nearly arbitrary form, while ensuring that you can reason abstractly about these 6 topics. So I've been assured by an ornithologist that that's what an owl looks like when it's reasoning abstractly. So we introduced TLMs into Reason, another convenient name for a language where I'm working in, adding this stuff to. It's really not fundamental. Reason is this thing that gives OCaml kind of an alternative, more like curly brace and semicolon style notation. So that's what I'll use, but you don't have to agree with the design decisions in that language to understand this. Okay, so let me give you an overview of TLMs. Again, we're assuming a bunch of libraries are imported. We're going to use this HTML running example. And that in yellow there is a TLM application. And each application of a TLM consists of 2 parts. There's a generalized literal form where your notation sits. And each generalized literal form consists of these outer delimiters. In our design, it's backtick parens. And then a literal body. And from the perspective of the context-free syntax of the language, that literal body is just an arbitrary character sequence, kind of like a string literal. It's constrained only in that any instances of backtick parens inside have to be balanced. And so that's just so that you can nest TLM applications within splices if you want to. And then the other part of a TLM application is a name, identifier of a TLM. I'm going to pronounce that lit TLM, that $ lit TLM, if you'll allow me. And so this TLM is what's responsible for expanding this literal body. And so that answers that first question of responsibility. We can just look at what was applied, and that's what's responsible. And there can't be conflicts because, again, we're explicitly applying things. So that's an easy answer to that question. Let me dig into actually how you go find that definition. So TLMs are part of the binding and scoping structure of the language. And so there's TLM abbreviations. That's an abbreviation. So lit HTML is actually equal to HTML notation.lit HTML. So it's just defined in this module HTML notation, which you can go to module in your editor or whatever and find that. And then in there is this notation definition. That's the definition of lit HTML. In there is a lexer and a parser, which are packaged together, and those are what are called to actually do the lexing and parsing and expansion. I'm not going to show you actually the details of that, but you use off-the-shelf lexer and parser generators in OCaml, OCaml-Lex and Menhir to implement these. The paper has a lot of details if you want to go look at that. But at the end of the day, there's this process at compile time of expansion, type expansion, that generates this expansion that you see there. Okay. So let's look at the next question, expansion typing. What is the type of the expansion? We could look at the expansion and answer that question or reason about the parser or code generation. But if we don't want to do that, if we hold those things abstract, how do we answer this question? Well, there's a type annotation on the notation definition. Okay, great. So context dependence. How do we figure out what needs to be imported, what dependencies the expansion has? We can look at the expansion again. Here we see it requires this library, this module HTML. And but if we don't want to look at that, if we hold that abstract, instead it's a little more difficult. So instead what we do is the notation definition has to explicitly list the dependencies that the expansions it generates might use. So here it just lists this module dependency HTML. It says internally I'm going to use the module variable HTML for this module HTML as it's defined at that notation definition in that where the notation definition is. And in fact, the system makes sure that that binding is exactly that binding as it exists at the notation definition site. So even if at the application site you had shadowed this module HTML, that would be fine. Actually, what would happen is the expansion would refer to the version of that HTML module defined at the HTML definition site. And so really, you don't even have to look at that list of dependencies as a client. That's just something for the system to see. You can reason abstractly about context dependence because it's just context independent guaranteed. And then, okay, let's talk about segmentation. Where are the splice expressions? This one's tricky because even if you look at the expansion, you can't really tell what the relationship is between parts of that expansion and the character sequences in your source file. So you'd have to really go look at the implementation of your parser to do this manually. We don't want that. And so this process of expansion actually consists of two phases. It's not just, the whole thing consists of this first phase, which is proto-expansion generation. That's what the parser generates. And a proto-expansion differs from expansions in that the splices are represented with these splice references by their position in the literal body. So characters 13 through 17 are the splice expression name. And if you can communicate to the programmer just this set of splice references, holding everything else abstract about the proto-expansion and the final expansion, then they'll know where the spliced expressions are. And so how do you communicate that to the user? Well, one way to do that is to color spliced expressions differently from the rest of the literal body. So here the spliced expression is black, everything else is green. The system ensures that all splice references are non-overlapping and actually separated by at least one character, so that this kind of coloring can be uniquely generated and uniquely conveys this segmentation, the set of splice references. So there is a little bit, you need a little bit of help to be able to reason about segmentation, but this is the kind of thing that, by looking at the thing presented to you, you can reason about segmentation. And then segment typing, you might have noticed there's a type annotation on each segment that could also be communicated to you by just showing you that somehow in a pretty printer or in your editor. And then finally, capture. Where are the variables and splices bound? We want to be sure that this variable name is actually bound to that argument name. But what if that proto-expansion had its own binding of name in it? That could accidentally cause weird things to happen. And so splicing in the TLM system is capture avoiding. So you can think of that as, the splices are inserted into the expansion using capture avoiding substitution, or you can think of that as all these internal bindings are implicitly alpha renamed. And so you can see it was changed to name prime, and so name now refers correctly in the final expansion. So that's it. That's this more reasonable mechanism. You can express all sorts of different literal notations because the literal body is really unconstrained. It's not even lexed ahead of time. Yeah, our owl is reasoning abstractly very happily. This set of reasoning principles, I think it's a really useful sort of rubric to analyze other mechanisms that people have for defining new notations and even other sort of code manipulation things. So for example, in OCaml, people use PPXs sometimes. These are preprocessors that look at these annotated ASTs and they'll go and rewrite them. And this sort of addresses the responsibility problem in that there's like a name there, but that name is just like a token. There's no scoping, there's no abbreviations that you can do for that. So kind of addresses responsibility, but none of the other reasoning principles. Template Haskell has this quotation system that has proper responsibility, but you can't abstractly reason about typing and binding and so on. It's the same thing with unhygienic term rewriting macros in various languages like Lisp, various Lisps. And with hygienic term rewriting macros, and typed ones like in Scala, for example, you can reason about responsibility and typing, and the hygiene mechanism allows you to reason about context dependence. But if you tried to use one of those mechanisms to just rewrite a string literal, splicing wouldn't be possible because that variable name that comes out, the hygiene mechanism is going to be like, where'd this come from? This isn't, you're not allowed to use this variable. And so it's really the mechanism of this proto-expansion stuff that I showed you. That's really the way that you allow arbitrary parsing of literals in these macro systems. So you could use some of the mechanisms that are available in hygienic term rewriting systems to override the hygiene to very carefully implement a literal macro system. And I hope somebody that's in that community does that. But you can't, you can't naively do that. So in the paper, so those were just kind of informal statements of the reasoning principles. In the paper, we have a formal specification of the TLM system as a type lambda calculus. Is the main, I'm not going to give you all the details, obviously, but the main judgment looks like this. It's a type expansion judgment. It starts from an unexpanded expression e hat, which has a literal form, literal bodies in it, just unparsed. And then it expands to an expanded expression, which is just a normal expression. And then there's this TLM context, which contains all the definitions of the TLMs. And the purpose of this is, one, to make precise this mechanism, how it works. And two, we can prove a reasoning principles theorem. And I'm not going to go into all the details here, but you can see that there's 6 clauses in this theorem corresponding to the 6 reasoning principles that I just talked about. So if someone wants to look at this in more detail, I'm happy to sit and talk about how this works later on. Also, there's a few other things in the paper. So I've been talking just about expression TLMs. You can also have pattern TLMs that generate patterns instead of expressions. There's a little bit of a difference in how reasoning about binding works, obviously, because patterns introduce bindings instead of consume them. And so that's the details are in the paper. You can see an example there. There's a few conveniences in the paper. For example, this open notation thing. If you're repeatedly applying the same TLM, like in all of the clauses of this pattern match, you can open that notation and it will be applied implicitly if you don't explicitly apply something. And so that gets you this nice, concise pattern match here. And then I've been talking about like things at a single type, like HTML.t, but if you have a module type set that you can define many different implementations of set, like hash set and so on. You can define a single TLM that's parameterized over all modules S that have this signature set, and also over all types of the set elements. And yeah, just define that notation once and then instantiate this TLM for different implementations of set. So it's kind of like a functor for notation, and that's in the paper as well. I won't show you too much about that. So to summarize, literal notation is an important part of the UI that a programming language presents to the programmer, but I think less appreciated is that the reasoning principles that the language gives you, which really form the mental model that you have, are also an important part of the UI that the programming language gives you. And so TLMs are really designed to allow you to define new literal notation and reason in an abstract manner about what you see in your client programmer. So we have an implementation of this. It's called Realit, and it's available there at GitHub. This is kind of a beta, but like you can go and play with this in in Reason today and define your own expression TLMs right now. And we have a talk at the OCaml workshop on Thursday that's more of a deep dive into how the implementation works. So if you've noticed, I've been telling you that there's all this integration into the bindings and type structure of OCaml and the module system and everything, but we didn't modify OCaml semantics itself to do that. Instead, we just added a little bit of notation to the parser, and then we used some encoding tricks. We used singleton signatures and things like that to encode TLM definitions and applications. And then we just defined a little preprocessor that implemented TLM. So Charles, who's a really bright undergrad that I've been working with at Chicago, is going to be giving a deeper dive and a live demo of Realit at the OCaml workshop on Thursday. And then I just want to briefly mention some ongoing kind of future work related to this that we're working on in the Hazel project, which is my main project, which I'll be talking about at Strange Loop on Friday. So you can imagine, so this whole paper was about if your notation is text. But what if your notation, what if you want to construct something by interacting with a graphical user interface directly within your program? So you have a left binding and you want to construct something of type list of student records with a UI. So we're working on this thing called live palettes, where you can do that. You can define these new UIs specific to different types, much like TLMs, but it's not text, it's a UI. And splices correspond to holes in the UI that you can fill with arbitrary expressions, including with other palettes, for example. And so I'll give you a little bit more on that at Strange Loop on Friday, and there's you can see a little more at hazel.org. So I'll leave those links up, and 5 seconds left. All right, awesome. I will take questions.
Well, first question, people are very excited to hear about error messages.
Yeah. Right. So the parser it can report error messages in the literal body. Obviously, the HTML parser is going to report HTML errors. If there's a type error in a splice, the fact that each splice has a type annotation allows you to say what the expected type was without referring to the whole expansion. If there is a, and then the context independence and capture avoidance stuff allows you to, so yeah, the abstract reasoning is also allows the error messages to be reported abstractly in terms of the surface in general. The only kind of caveat is if there's an error in the code generated by the TLM, which in OCaml is not guaranteed at definition time to be well typed, that could cause, if your TLM's broken, those errors can get pretty gnarly. The paper, I didn't mention, the paper also has a little section on if you use meta OCaml to define the parser, you can actually get rid of that class of errors as well. And so that's kind of an experimental thing that we're working with. And so, yeah, so we're working in Realit on better error messages, but I think these reasoning principles are also relevant to the problem of error reporting in that way.
How do these notations compose? So, you might have CSS blocks inside HTML blocks or headers inside URLs. So,
yeah, so I mean, splicing is the main composition mechanism. So you go from this like HTML notation to an arbitrary expression of your language, and then there you can then apply the lit CSS and get some CSS. And then obviously the parser can be defined such that it calls into another parser internally if it wants. But yeah, you always do this kind of like out and back in kind of thing to do composition.
Have you evaluated using something like types to help direct that? Maybe I know that I'm looking for a CSS thing at a particular point.
Yeah. So we have another paper it was at eCoop in 2014 where we had a mechanism for using types to actually invoke something like a TLM. It didn't have quite all the reasoning principles that are the focus and novel contribution of this paper. But in a bidirectionally typed language, without Hindley-Milner style type inference, that works. It didn't quite work in OCaml when we tried it. So we have this implicits that I showed you, but it's context free. Yeah.
Okay. So I'm going to read this question out. Programmable and variable concrete syntax is credited as being one of the reasons for the non-success of Algol 68. Which considerations are in favor of programmability by library designers of literal syntaxes in TLM?
Okay. Well, I don't know about the history of Algol's adoption. Yeah, I think if you look at a lot of the mechanisms that people have proposed, they've really been library provider focused. How do we empower the provider to do something, whatever, extend the language in whatever way they want? And I think it's really this rubric that I showed that people, were maybe like implicitly like, oh, I don't like extensibility because I don't like that I can't reason about these things. And so I think focusing in this mechanism and in future mechanisms on abstract reasoning is really, I mean, it's a hypothesis. Relit's out there. Hopefully, we'll get a lot of interest, and we'll see how extensibility plays out in language design in the future.
Have you considered allowing these templates to be themselves programmer generated in some way, so you get something closer to a full-blown macro system?
The outer delimiters, you mean?
Yeah. The strings.
I'm not sure I understand that question. Have we considered allowing what to be programmer generated?
The strings that are then going to be interpreted by the TLM parser.
Oh, I see. I think right now you can have TLMs in the output in Realit. That's one way to do kind of multi-stage stuff. And I should say that these things, like, there's other ways of extensible syntax, like adding new infix operators. Those are complementary. We're not replacing those things. This is for literal forms, which are delimited. And I think other mechanisms for metaprogramming are also complementary. This isn't meant to subsume be the only mechanism for metaprogramming in the language. And so you could have other types of term rewriting macro systems or staging macros or something that generate things with TLMs in them. Yeah.
All right. Well, thanks, Iris, again.
All right. Thanks.